NENOMATICA, where mathematics meets YouTube excellence. Fifth law of power. In this video, we'll prove that any non-zero number raised to the power of 0 equals 1. The rule states that for any non-zero number, a to the power of 0 equals 1. Let's understand why this is true by looking at the values in a table. In the image, we can see the results of calculating 3 raised to different powers. We can observe a pattern here. When we decrease the exponent by 1, the result is divided by 3. For example, 3 to the power of 4 is 81, and 3 to the power of 3 is 27. If we divide 81 by 3, we get 27. Similarly, 3 to the power of 3 is 27, and 3 to the power of 2 is 9. 27 divided by 3 is 9. And again, 3 to the power of 2 is 9, and 3 to the power of 1 is 3. 9 divided by 3 is 3. If we continue this pattern, we should look at what happens when we go from 3 to the power of 1 to 3 to the power of 0. 3 to the power of 1 is 3. If we divide by 3, following our pattern, we get 1. So 3 to the power of 0 equals 1. In this video, we'll explore an important rule in exponent laws that states, any number raised to the power of 0 equals 1, as long as the number is not 0 itself. The rule can be written mathematically as, for any non-zero value of a raised to the power of 0 equals 1. According to the laws of exponents, when any number is raised to the power of 0, that equals 1. Now, let's prove this theorem using the laws of exponents. We'll start by examining how exponents work when dividing powers with the same base. When we divide numbers with the same base, we can use the quotient rule of exponents. This rule states that when dividing powers with the same base, we subtract the exponents. Let's consider the expression a to the power m divided by a to the power m, where it is any non-zero number, and m is any exponent. Using the quotient rule of exponents, we can rewrite this as a to the power m minus m. Simplifying m minus m, we get 0. So our expression becomes a to the power 0. At the same time, we know that any number divided by itself equals 1, as long as the number is not 0. So a to the power m divided by a to the power m is equal to 1. Now we have two valid expressions for a to the power m divided by a to the power m. From steps 3 and 4, we can write that a to the power 0 equals 1. There's another way to look at this. We can also consider the division of same powers as the ratio of those powers. We can write a to the power m divided by a to the power m as a fraction. This equals a over raised to the power m. Since a divided by a equals 1, for any non-zero, this expression becomes 1 to the power m. And 1 raised to any power is always 1, so our expression equals 1. Combining this result with our earlier finding that a to the power m divided by a to the power m equals a to the power 0, we can conclude that a to the power 0 equals 1. Therefore, we have proven that for any non-zero number, a raised to the power of 0 equals 1. This is an important rule in mathematics that helps us simplify expressions involving exponents. Let's look at some examples to verify this rule. For our first example, let's calculate 2 to the power of 0. According to our rule, this should equal 1. Similarly, for 10 to the power of 0, we also get 1. Even for negative numbers like -5 to the power of 0, the result is still 1. It's important to note that this rule only applies when the base is not 0. The expression 0 to the power of 0 is undefined in standard mathematics because it leads to contradictions in different contexts. To summarize, the zero exponent rule tells us that any non-zero number raised to the power of 0 equals 1. This rule follows directly from the laws of exponents and is consistent across all areas of mathematics. Let's look at our first example. We need to calculate -5 raised to the power of 10 multiplied by 5 raised to the power of 6. First, let's analyze what happens with the -5 raised to the power of 10. Since the exponent is even, the result will be positive. We can rewrite this as 5 raised to the power of 10. Now, we can apply the product rule of exponents. When multiplying powers with the same base, we add the exponents. So we add the exponents 10 plus 6 to get 5 raised to the power of 16. Let's move on to our second example. Here we have negative 5 raised to the power of 11 times 5 raised to the power of 4, all divided by 5 raised to the power of 3 times negative 5 raised to the power of 7. Let's rewrite this expression more clearly. We have the fraction with numerator negative 5 raised to the power of 11 times 5 raised to the power of 4, and denominator 5 raised to the power of 3 times negative 5 raised to the power of 7. For the negative 5 terms, we need to be careful with the negative sign. When negative 5 is raised to the power of 11, the result is negative because 11 is odd. And when negative 5 is raised to the power of 7, the result is also negative because 7 is odd. So the signs will be important here. Now we'll work with the exponents. Let's separate the negative signs and rewrite our expression using positive bases. We get negative 5 to the power of 11 times 5 to the power of 4, all divided by 5 to the power of 3 times negative 5 to the power of 7. Let's simplify this further. We can rearrange this as negative 5 to the power of 11 times 5 to the power of 4, divided by 5 to the power of 3 times negative 5 to the power of 7. This gives us negative 5 to the power of 15, divided by negative 5 to the power of 10. Since the negative signs appear in both numerator and denominator, they cancel out. Then we can use the division rule for exponents to get 5 raised to the power of 15 minus 10, which equals 5 raised to the power of 5. Now, let's tackle our third example. We have negative 2/3 raised to the power of 4 times 2/3 raised to the power of 5 times negative 2/3. First, let's handle the negative sign in negative 2/3 raised to the power of 4. Since 4 is even, the result will be positive. So this term becomes 2/3 raised to the power of 4. For the last term, negative 2/3 raised to the power of 1, this is just negative 2/3 itself. Now we can use the product rule of exponents to combine all the terms with the same base, which is 2/3. The negative sign will stay outside. Adding the exponents, we get 4 plus 5 plus 1, which equals 10. So our final answer is negative 2/3 raised to the power of 10. Let's examine our first rule. When a negative number is raised to an odd power, the result is always negative. Mathematically, this means that if we have negative a raised to the power of 2k plus 1, where k is any integer, the result is negative a to the power of 2k plus 1. For example, let's look at negative 5 cubed. Since 3 is odd, the result will be negative. We calculate this by multiplying negative 5 3 times, negative 5 times negative 5 times negative 5. So negative 5 cubed equals negative 125, a negative number. This confirms our rule. When a negative number is raised to an odd power, the result is negative. Now, let's look at our second rule. When a negative number is raised to an even power, the result is always positive. Mathematically, this means that if we have negative a raised to the power of 2k, where k is any integer, the result is simply a to the power of 2k, which is positive. Let's see an example of this. Let's calculate negative 5 squared. Since 2 is an even number, the result will be positive. We calculate negative 5 squared as negative 5 times negative 5. When we multiply two negative numbers, the negatives cancel out, and the result is positive. So, negative 5 squared equals 25, a positive number. This confirms our second rule. When a negative number is raised to an even power, the result is positive. Before we dive into specific examples, let's recall the fundamental laws of exponents that we'll need. The first law we'll use is the product rule for exponents, which states that when multiplying terms with the same base, we add their exponents. For example, a to the power of m times a to the power of n equals a to the power of m plus n. The second important concept to understand is that when a negative number is raised to a power, the sign of the result depends on whether the exponent is even or odd. If the exponent is even, the result is positive. If the exponent is odd, the result is negative. Now, let's work through our first example. We'll simplify the expression negative 10 times negative 10 squared times negative 10 cubed times negative 10 to the fourth power times negative 10 to the fifth power times negative 10 to the seventh power. Let's begin by rewriting the expression. We can rewrite negative 10 as negative 10 to the first power to better see the pattern. Also, remember that when a negative number is raised to an even power, the result is positive, and when raised to an odd power, the result is negative. So negative 10 squared equals positive 100 since 2 is even, and negative 10 cubed equals negative 1000 since 3 is odd. For the fourth power, it's positive again, and so on. Let's rewrite each term based on these rules. Now we have negative 10 times positive 10 squared times negative 10 cubed times positive 10 to the fourth times negative 10 to the fifth times negative 10 to the seventh. Let's continue simplifying. We can further rewrite this in a different way. The negative 10 to odd powers can be written as negative 1 times 10 to that power. And for all the even powers, we simply have 10 to that power. So our expression becomes negative 10 times 10 squared times negative 10 cubed times 10 to the fourth times negative 10 to the fifth times negative 10 to the seventh. Now, let's handle the negative signs. We have negative 10, which is negative 1 times 10. Then we have 10 squared. 4 negative 10 cubed, that's negative 1 times 10 cubed. Then we have 10 to the fourth. 4 negative 10 to the fifth, that's negative 1 times 10 to the fifth. And finally, negative 10 to the seventh is negative 1 times 10 to the seventh. Now, we can count the number of negative 1 factors. We have 4 negative 1 factors in total. Since an even number of negative 1s multiplied together gives positive 1, the result will be positive. Let's now focus on the powers of 10. We have 10 to the first, 10 squared, 10 cubed, 10 to the fourth, 10 to the fifth, and 10 to the seventh. Using the product rule for exponents, we add all these exponents. 1 plus 2 plus 3 plus 4 plus 5 plus 7 equals 22. So our final answer is 10 to the power of 22. Let's move on to our second example. We'll simplify the expression negative a squared times negative a cubed times a to the fourth power times negative a to the fifth power. Let's start by analyzing each term. For negative a squared, we know that when a negative is raised to an even power, the result is positive. So negative a squared equals a squared. For negative a cubed, since the exponent is odd, the result remains negative. For a to the fourth power, it's just a to the fourth. And for negative a to the fifth power, the exponent is odd, so the result remains negative. Now, let's rewrite our expression based on these observations. We have a squared times negative a cubed times a to the fourth times negative a to the fifth. Now, we need to handle the negative signs. We have 2 negative signs in our expression, and since 2 negatives multiply to give a positive, the overall sign will be positive. Now, let's focus on the powers of a. We have a squared, a cubed, a to the fourth, and a to the fifth. Using the product rule for exponents, we add all these exponents. 2 plus 3 plus 4 plus 5 equals 14. So our final answer is a to the power of 14. Let's tackle our third example. We'll simplify the expression negative a cubed times negative a to the fourth power times negative a to the fourth power times negative a cubed times a to the sixth power. Let's start by analyzing each term as we did before. For negative a cubed, since the exponent is odd, the result remains negative. For negative a to the fourth power, the exponent is even, so the result is positive, which is just a to the fourth. We have another negative a to the fourth, which is also a to the fourth. Then we have negative a cubed, which is negative since the exponent is odd. And finally, a to the sixth power remains, as is. Let's rewrite our expression based on these observations. We have negative a cubed times a to the fourth times a to the fourth times negative a cubed times a to the sixth. Now, we need to handle the negative signs. We have 2 negative signs in our expression, and since 2 negatives multiply to give a positive, the overall sign will be positive. Let's focus on the powers of a. We have a cubed, a to the fourth again, a cubed again, and a to the sixth. Using the product rule for exponents, we add all these exponents. 3 plus 4 plus 4 plus 3 plus 6 equals 20. So our final answer is a to the power of 20. Let's summarize the key points we've learned today. First, when dealing with negative numbers or variables raised to powers, remember that if the exponent is even, the result is positive. If the exponent is odd, the result is negative second. When multiplying terms with the same base, add the exponents. And finally, always count the number of negative factors to determine the final sign of your answer. These rules will help you solve problems involving exponents and negative numbers efficiently. As a challenge, try this problem on your own. Simplify -2 cubed times -2 to the fourth power. Pause the video, solve it, and then continue to check your answer. The answer is -32. Great job if you got it right. Let's start with our first example. We need to evaluate this expression. 2a times 3a squared times 4a cubed times 5a to the fourth times -2a squared times -a cubed to the fifth power. Let's solve this step by step. First, let's expand the power expressions. For -2a squared, we get 4a to the fourth power. Next, we'll expand -a cubed to the fifth power. Since -a cubed has a negative sign, and we're raising it to the fifth power, we get -a to the 15 power. Remember, when we raise a negative number to an odd power, the result remains negative. Now, let's separate the coefficients and the variables to make our calculation easier. We get 2 times 3 times 4 times 5 times 4 times -1, multiplied by a to the first power times a squared times a cube times a to the fourth times a to the fourth times a to the 15th. Finally, let's calculate the coefficients and add the exponents. For the coefficient, we get -480, and for the exponents, we add all the powers of which gives us a to the 29th power. So our final answer is -480a to the 29th power. Let's move on to our second example. Here we have -a squared times -b cubed times -a to the fourth times -b to the fourth times -c to the fifth times -c squared times -a. Let's solve this step by step. First, let's evaluate each term separately. -a squared equals +a squared because a negative number squared is always positive. Let's continue evaluating each term. -b cubed equals -b cubed since raising a negative to an odd power keeps the negative. -a to the fourth equals a to the fourth, since raising a negative to an even power gives a positive result. -b to the fourth equals b to the fourth. -c to the fifth equals -c to the fifth. -c squared equals c squared. And finally, -a remains -a. Now, let's group like terms and calculate the result. We get -a to the seventh times b to the seventh times c to the seventh power. We can rewrite this in a different form. Our expression equals -a times b times c, all raised to the seventh power. Let's look at our third and final example. Here we have a squared cubed times a cubed squared times -b cubed to the fourth times -c squared to the sixth times, abc cubed times abc squared. Let's solve this step by step as well. First, we evaluate each expression with nested exponents. A squared cubed equals a to the sixth. A cubed squared equals a to the sixth. For -b cubed to the fourth, we get b to the 12th since the negative raised to an even power becomes positive. For -c squared to the sixth, we get c to the 12th for the same reason. Now, let's combine the like terms. We have a to the sixth times a to the sixth, which gives us a to the 12th. We also have b to the 12th and c to the 12th, along with abc cubed and abc squared. Let's continue simplifying. We can rewrite this as abc to the 12th times abc to the 5th. Finally, we combine the exponents to get our answer. This gives us abc to the 17th power. Let's summarize what we've learned about evaluating expressions with exponents. First, when we raise a power to another power, we multiply the exponents. Second, when we have a negative base raised to a power, the sign of the result depends on whether the exponent is even or odd. Third, when multiplying terms with the same base, we add the exponents. Finally, we can factor out common bases and combine their exponents. By understanding and applying these rules, you can evaluate complex expressions involving variables with exponents. Remember to work methodically, evaluating one term at a time and combining like terms at the end. Let's solve the following problem. We need to simplify this complex expression and express it as a single power. Step 1. Rewrite the expression using properties of exponents. First, let's rewrite each term of the expression. We have 5 times a to the -7. For the second term, we need to use the power rule. 2a raised to the 5th power becomes 2 to the 5th times a to the 5th. Similarly, for the third term, 2a raised to the negative second power becomes 2 to the negative second times a to the negative second. And for the last term, negative a squared, raised to the second power, we get a to the fourth. Step 2. Simplify the constants that don't involve the variable a. Let's calculate 5 times 2 to the fifth power times 2 to the negative second power. 2 to the fifth is 32. 2 to the negative second is 1 over 4 or 1/4. So we get 5 times 32 divided by 4, which equals 40. Step 3. Let's apply the product of powers rule to combine all the powers of a. According to this rule, when we multiply powers with the same base, we add their exponents. So we have -7 plus 5 plus -2 plus 4. Let's calculate this sum. -7 plus 5 is -2. -2 plus -2 is -4. And -4 plus 4 equals 0. Step 4. Now we need to simplify the power of a. Remember the important rule that any non-zero number raised to the power of 0 equals 1. So a to the power of 0 equals 1, and we get 40 times 1. Finally, we get our answer. 40 times 1 is just 40. So the complex expression 5a to the -7 times 2a raised to the fifth power times 2a raised to the negative second power times negative a squared raised to the second power simplifies to just 40. In this video, we'll explore the concept of exponential expressions and determining their domain. Let's start with an important note about 0 to the power of 0. When it equals 0, the expression a to the power of 0 is undefined. Let's consider our example. We have the expression 7x to the power of 4 minus 7 raised to the power of 6 minus 6x squared. For what values of x is this expression defined? We need to check two things. First, let's find where the exponent 6 minus 6x squared equals 0. This is important because if the base equals 0 and the exponent equals 0, we'll have 0 to the power of 0, which is undefined, as we noted earlier. Let's solve this equation. We can factor out 6 from the left side, giving us 6 times 1 minus x squared equals 0. Dividing both sides by 6, we get 1 minus x squared equals 0. Rearranging, x squared equals 1. Taking the square root of both sides, we get x equals plus or minus 1. Next, let's find where the base 7x to the power of 4 minus 7 equals 0. We can factor out 7 from the left side, giving us 7 times x to the power of 4 minus 1 equals 0. Dividing both sides by 7, we get x to the power of 4 minus 1 equals 0. Rearranging, x to the power of 4 equals 1. Taking the fourth root of both sides, we get x equals plus or minus 1. Now combining our results, we see that at x equals plus or minus 1, both the base and the exponent equal 0. This means at these values, the expression would be 0 to the power of 0, which is undefined. Therefore, the domain of the expression is all real numbers except -1 and +1. In set notation, the domain is R minus the set containing -1 and +1. Let's visualize this domain on a number line. It includes all real numbers except for the points at -1 and +1, which are excluded because they would make our expression undefined. In summary, when determining the domain of exponential expressions, we need to check for cases where we might get 0 to the power of 0, which is undefined. For this specific expression, we exclude x equals plus or minus 1 from the domain. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.